So I was thinking that what to do in 22 minutes, because there is a statistics. This is the first lecture I think on statistics as far as the bioinformatics conference is concerned. But I would like to give you some idea. For example, what are the statistical tests which can be used for genetic association studies? So my focus will be on that basically. So I will try to finish in 20 minutes maybe. And if there are any questions, then I will be answerable to that. So this is the content of my talk. First of all, I would like to discuss something about the different type of data, because most of the people, they make mistakes whenever they perform analysis if they don't recognize the data in a proper way. Then normality and outlier check, how to do in using statistical tools. Then basic statistical techniques. I will not discuss much on the basic statistical techniques. Then measures of association that I will take up. And disease prediction model. Of course, there are many prediction models, but I'll just look into the disease prediction model, basically the logistic regression, and the odds ratio, risk ratio, sensitivity, specificity, and ROC curve. Along with that, there is an important statistical test, which is called sequential kernel association test, which is called SCAT procedure, to find out the association between genotypes and phenotypes in presence of the covariates. So that will be the crux of the entire talk. So let me look at the nature and types of data. If you look at the nature of data, any type of data is either called as structured data or it is called unstructured data. Professor GPS Raghav in the morning has given you some idea about structured and unstructured data. Structured data is the one which can be highly organized, and you can extract features, you can extract patterns out of that, but that is not possible for unstructured data. Unstructured data is basically involving audio, video, social media information, and all this. And what is a big data? Big data is sometimes the mixture of the two, the structured and unstructured data. Now, if you look at the structured data, it is of two types. Either it is called the categorical data or it's called the measurement data. What do you mean by categorical data? Where the measurements are in terms of categories. For example, ethnicity, Asian, European, American, I can call 1, 2, 3. Similarly, male, female, I can write 1 and 2. And what is a measurement data means some kind of instrument is being involved in measuring something. But here there is something important, scales. Before you subject any data to statistical analysis, you should be very clear about the knowledge about these scales. If you are dealing with categorical data, that means the measurements are in terms of categories like 1, 2, 3. Then it is always in terms of two scales. One is called the nominal scale, another is called the ordinal scale. Now, what do you mean by nominal scale? In nominal scale, all categories are given equal weightage. For example, if you look at gender, so everybody is same, everybody is human being. I can write male as 1, female as 2, or you can write female as 1, male as 2, doesn't make any difference. So if there is equal weightage to each and every category, then we say that our data belongs to the nominal scale. And what is an ordinal scale? Ordinal scale means you have the categorical data, but you can arrange the categories either in ascending or descending order of magnitude. For example, say socioeconomic class, lower class, middle class, upper class, you can arrange the categories in order. Similarly, if you look at the, let's say, severity of disease, mild, moderate, severe, you can arrange the categories in order. So these two scales, nominal and ordinal, they are basically referring to the categorical data. And you have to be very careful, because statistical methods which have been designed to deal with the categorical data, they cannot be applied for measurement data. Of course, with certain expertise, you can, but you need to have some kind of expertise. Okay, now if you look at the measurement data, it is also in terms of two scales. One is called the interval scale, another is called the ratio scale. What do you mean by interval scale? In interval scale, sometimes the mathematical operations are not valid. And there are many types of data where mathematical operations are not valid. Let's say, look at the intelligence. Suppose one student has scored 90 marks in a test. Another student has scored 30 marks in a test. Now, if you divide 90 by 30, answer will be 3. But you cannot make a statement that the student having 90 is exactly the 3 times the intelligent than the student having scored 30. You cannot make such type of statements, right? Mathematically, it is not correct. So if you come across data like temperature, for example, in interval scale, 0 always has a meaning. For example, if I say temperature 0, that means it doesn't mean the temperature is absent, right? If somebody has scored 0 in a test, it doesn't mean the person is not intelligent at all. So it is, that's why in interval scale, the 0 is always taken as an arbitrary 0, while in ratio scale, 0 is the actual 0. So that's the difference between interval and ratio scale. If you look at the ratio scale, let's say somebody is having weight, say 80 kg, another person is having 40 kg, and if I divide, the answer will be 2. But you can always make a statement that the person having weight 80 kg is double the weight of the person having weight 40 kg. So nothing wrong with that. So like height, weight, etc., they all in terms of ratio scale, and interval scale like intelligence score, beauty score, temperature, etc., they all go to the interval scale. So you have to be very, very clear about the knowledge of these scales, because many of the softwares like R, you have to R, if you are dealing with R, they will ask you about the categorical data, that is called a factor in R. So you have to be very careful. Okay, now who are the founders of modern mathematical statistics? If you look at the correlation and regression, that was discovered by Carl Pearson's correlation coefficient, and most of the bioinformatics people, they are using that. P-value and testing by R. A. Fisher, confidence interval approach by Neyman, and also if you look at the estimation and testing using confidence in the interval approach, that by Pearson. And there are two great Indian statisticians. One of them is Mahalanobis. Mahalanobis has established Indian Statistical Institute in Calcutta in 1934, and one of the great person on this earth right now. He is completing 100 years on the 10th of September. He was born in 1920, and everybody knows his name. Very well-known statistician in India and America. He is working as a professor emeritus at Pennsylvania State University, and US president had honored him with a National Medal of Science in 2002, and his name is Professor C.R. Rao. We are celebrating his century birthday this 10th of September. So very renowned person, known for Rao-Blackwell theorem and many of the multivariate techniques. Okay, now major problem comes whenever we subject our data to statistical analysis, how to check the normality of the data. So there are three basic graphical procedures. One of them is histogram. You can look at the shape of the histogram. It is more or less symmetrical. You can say data is having a normal distribution. And then you can otherwise you can look for the box plot. And box plot, if median is there in the center, again you can see that the data is normally distributed. But third most important graph is called the normal quantile plot, or sometimes called QQ plot. So it plots the quantiles of your data against the quantiles of the standard normal, and if the points are along a straight line, then we say that our data follows normal distribution. And sometimes you are in a fix whether I should take this graph symmetrical or not to take this graph as symmetrical. Then there are two important tests to check the normality of the data. One of them is called KS test, which is called Kolmogorov-Smirnov test, and another one is called Spirovic test. So if you look at the shape of this histogram, you can see that if you drop a line from the largest bar, there are only 3 bars on the left-hand side, but many bars on the right-hand side. So you can see this is a normal curve. If this would have been normal, all the entire bar should have been within this curve, but it is not. So what we confer that it is not following a normal distribution. This is almost approximately following a normal distribution. And if you look at the box plot, the median is not there in the center. Then the lower area is less and upper area is more. So obviously this is positively skewed. Similarly for this, but box plot can identify outliers. If there is any outlier, it can identify with the help of, it can be identified with the help of box plot. And this is the normal quantile plot. You can see there are some deviations here, some deviations here. So data is not following exactly the normal distribution. Okay, now this is one aspect if you are dealing with the univariate data, but sometimes we have to deal with the thousands of variables together. Then how to find out the outliers present in your data? Then there is a technique which is called Mahalanobis distance. I have just told you about the picture of the Mahalanobis, and he has discovered this, that you look at this vector and then there is a threshold point. If it crosses that threshold point, so it will be marked separately, and you can find out that in this variable 1 and variable 2, I have just taken a simple demo, this is considered to be an outlier. So for any multivariate data, outlier is possible to detect with the help of Mahalanobis distance. Now, these are some of the basic techniques. If your data is normal, you can use mean, etc. But if data is skewed type of data, you cannot use mean, then we have to use median, applications of median, etc. Many probability distributions are there which can solve problems related to statistics like binomial, Poisson, normal. Now, most of the people in bioinformatics, they use Carl Pearson's coefficient, Spearman's rank correlation coefficient, but some of them are not very well aware of that they cannot be used for categorical data as such, right? So I will discuss in 1 or 2 minutes that what are the different type of correlations or different measures of association which can be computed if there is a categorical data. Then people also go through the different kind of regression techniques. Regression means if you are dealing with only two variables, then it is called a simple regression. If you are dealing with one dependent variable and rest of them independent variables, then it is called a multiple regression. Then there is a survival analysis, logistic regression. In logistic regression, you can use categorical data as well as measurable data. Both of them are possible. Then people also use one-way analysis of variance. One-way analysis of variance technique is applicable whenever you want to compare more than 2-3 categories. Similarly, two-way ANOVA, if your, let's say, outcome is dependent upon two factors at the same time. Say yield of a crop depends upon the amount of fertilizer used and amount of rainfall. So it depends upon two factors, right? So in that case, you can use two-way ANOVA. Then Krusikal Wallis and one-way ANOVA and Friedman, they can be used if your data is not normal, because one-way and two-way can be used if data is normal. But if it is not, then we have to use Krusikal Wallis or Friedman test. They are in fact analog of one-way and two-way ANOVA. Then as far as estimation and testings are concerned, people are very much aware of t-test, f-test, chi-square test. I will not discuss all this, but they can be used. Let's say I'm looking at a testing of, for example, can I say that FPKM value, which is called fragment per kilogram per million, is equal to 50 or not? So I can use for a particular region. So I can use one sample t-test. And if you want to compare between two different regions, you can use two sample t-test. And also if you have before and after situation, you can use pair t-test. Even for correlation testing, you can use t-test. So all these are tests which can be handled with the help of t-statistics. But the important point is these can be applied only when your data is normally distributed. If it is not, then there is a non-parametric test. For example, for if there is then there is a Wilcoxon signed rank test. For two sample problem, then there is a Mann-Whitney test. Then there is a paired matched pair Wilcoxon signed rank test. So all these are there, I mean, analogs in non-parametric test. And to test the equality of two variances, there is F statistics. For testing the independence or association, there is a chi-square test. Then there is one-way ANOVA, two-way ANOVA, and MANOVA, etc. Okay, not to go into much details, there are many non-parametric tests and they are applicable whenever our data is not normally distributed. They are analogs of parametric. Now, if you look at the different type of correlations, most of the bioinformatics people, they know Spearman's or rank correlation, right? And they are, you see, Spearman's correlation you can compute only when both X and Y, they are measurable quantities. But let's say one of them is categorical, another is measurable quantities. You cannot apply Karl-Pearson's correlation coefficient. And if your data is present in the form of a rank, let's say from the 5-point scale, Likert scale, or 7-point scale, you can use Spearman's rank correlation, right? But you cannot use if both of them are categorical variables or nominal variables. Then there are different type of correlation, which I'll discuss in next 2-3 minutes. And just bear with me, I'll give you a few examples where they are useful. Then there is another type of correlation, which is called multiple correlation. What is a multiple correlation? There is one dependent variable and rest of them are independent variables. For example, you can think of coronary heart disease, which depends upon cholesterol, which depends upon blood pressure, which depends upon age of the person. So in that type of situation, you can use a multiple correlation coefficient. Then there is a partial correlation coefficient also. What is a partial correlation? Partial correlation means correlation between two variables, but it may be affected by some another variable which you need to control. For example, if somebody is looking at a relationship between age and blood pressure, but there may be smokers and non-smokers in your data. So you need to control the effect of smoking before looking into the actual relationship between age and blood pressure. For that purpose, we use what is called partial correlation. And now this Karl-Pearson's correlation coefficient, etc., they make sense only if there is a linear relationship between Y and X. But suppose there is no linear relationship, that means points must be along a straight line. But if there is no linear relationship, you cannot use Karl-Pearson's correlation coefficient. Then we have to make use of another correlation, which is called correlation ratio. And then if there is no visible type of pattern available, like whether it is increasing or decreasing, then there are lots of non-linear correlations and they are based on specific models. Okay, now if you have nominal by nominal, nominal means like gender, or you can say ethnicity, they are nominal. If you have nominal by nominal data, one variable is nominal, another is variable is nominal. You cannot compute Karl-Pearson's or Spearman's, etc. Then there are different type of correlation. You can compute contingency coefficient, phi and Kramer's law, and lambda coefficient. But the best one of this is uncertainty coefficient. That is the best one because it can give you direction also, whether it is negative or it is positive. Similarly, let's say you have ordinal by ordinal. One variable is ordinal, another is also ordinal. The gamma coefficient is the best. And when you have one variable as nominal, another as interval, then these are the coefficient to be computed. And out of this, kappa and Mach-Nehmer, they are the best coefficient to be computed in such type of situations. These are examples. Let's say nominal by nominal. Look at the example. Example is gender. Gender is a nominal. Blood types, they are also nominal. And you are looking at the relationship between them. Now, if you simply compute chi-square is always a positive quantity. You cannot get a complete idea whether it is association is decreasing, increasing, nothing like that. But if you are computing this lambda coefficient or uncertainty coefficient, it can come out to be negative and positive also. So in that situation, you can use this coefficients like uncertainty coefficient. Similarly for ordinal by ordinal examples, paternal age versus risk of disease. Risk of disease, mild, moderate, severe. So it's ordinal. Parental age can be put into, let's say 30 to 40 years, 40 to 50 years, and more than 60 years, something like that. And you can look at the, so this is all categorical. Similarly, if you have nominal by ordinal, you can apply Fisher's chi-square like AMD. AMD is called age-related macular degeneration versus the risk of disease. So AMD is either they are having or they are not having, 1 or 0. And risk of disease is mild, moderate, severe. So one is nominal, another is ordinal. So these are the coefficient to be computed. Similarly, nominal by interval, these are the coefficient to be computed. And by interval and ratio, you have number of choices for this. You can compute multiple correlation, you can compute partial correlation, you can compute Karl Pearson, Spearman, etc. Okay. And one of the important model is the disease prediction model, which is called logistic regression. In logistic regression, our dependent variable is always dichotomous. Of course, if you have more than 2 categories, then you can use multinomial regression. For example, this is the equation of a logistic regression. It comes from logistic function. Here, y is considered to be in terms of risk factors, that y is a combination of risk factors. So you can look at this graph. This is the graph of this px, and px always lies between 0 and 1. It's a probability. Probability always lies between 0 and 1. Now, what does this mean? Whenever a child is born, say 5-6 years, there is no risk. There is no diabetes. Generally, these things are not there. So what is the probability of dying of a young person is very, very low. But and when the age grows, the person is having diabetes, then X1, then person is having, say, blood pressure, X2, person is developing coronary heart disease, X3. So all these are risk factors. As the risk factors go on increasing, the probability that a person would die will go on increasing. And that is measured through what is called a logistic function, right? So Y is considered as a risk factors. So without going into the details, I don't have time. I'll just take a simple example to show you how this technique is applicable. For example, let's say your Z, which is a dependent variable, is coronary heart disease. Either people are having coronary heart disease or they are not having coronary heart disease. And coronary heart disease depends upon cholesterol, whether cholesterol is low or it is high. So you can code this as 0 and 1. This is called X1. So this is one of the dependent variable. Age you can put in years, and X3, ECG, whether it is normal or abnormal, again categorical. And then you develop this equation that Z is equal to this. Now these parameters can be estimated from the given data using maximum likelihood technique. And once you substitute in this equation, you can get the probability that what are the chances that a person is likely to have a coronary heart disease. So this is one of the disease prediction model based on the 609 cases. We have developed this equation. And if you use this for patient 1 with certain parameters like cholesterol, age, and ECG, these are given. And similarly for patient 2, and you look at the predicted risk. If you compute the predicted risk of the first patient, it is 73%. It is 35.5%. And if you divide, you will get risk ratio. So that means the patient who is having, this is patient number 2, who is having, let's say, high cholesterol level is likely to have the double the risk of the person who is having low cholesterol level. So these kind of predictions you can make it. And the odds ratio, people also get confused with the odds ratio. Odds ratio, let me give you a simple concept here. What do you mean by they are generally used in case control studies? Let's say this is exposed cases, non-exposed cases. You have cases and controls. You have A, B, C, D. These are the frequencies. You look at the odds of the exposure. A divided by C. This is all odd. Out of this, A plus C, how many total? Total is A divided by C. So odds of the exposure. Similarly, odds for control, B upon D. And if you want to compute the odds ratio, this is nothing but the cross product of A and D multiplied by B and C. So you can easily compute the odds ratio for any 2 by 2 table. And in case of the cohort studies, we do not compute the odds ratio. We always look at the risk, relative risk. Let's say this is a table, 2 by 2 table, exposed disease and not disease. And you look at the incidence of disease and C by, and then the risk ratio is given by the ratio of these two parameters in cohort studies. Okay, and one of the important correlation is called the Matthews correlation coefficient. Now, what is a Matthews correlation coefficient? It is based on a very important criteria, which is called sensitivity and specificity. Now, if you look at this table, these are the actual positive, these are actual negatives, and these are predicted by the test positive and predicted by the test negative. If they are correctly matched with each other, then this is called true positive. That actually they were positive, test also say they are positive, so it is true positive. But if they are actual negative and test also says they are negative, then they are true negative. And if test says they are positive, but actually they are negative, then this is called false positive. Similarly, this is false negative, right? And this is called PP is called the predictive positive. If you take the sum of these two, then this is called the predicted negative, and this is called the actual positive and actual negative. And based on this diagram, we look at the Matthews correlation coefficient. And first of all, we look at the sensitivity. Sensitivity is nothing but TP. TP is nothing but the true positive divided by the actual positive. So true positive divided by the actual positive, that will give you sensitivity. What is specificity? Specificity is true negative divided by the actual negative. And similarly, we can compute a positive predicted value, then the negative predicted value, they are given by this. And when all these values are known, you can substitute in this formula to get the Matthews correlation coefficients. And this interpretation is almost same as that of the Curl-Pearson's correlation coefficient, right? And based on the sensitivity and specificity, we can look at a very important curve, which is called the ROC curve. So why this ROC curve is important? Because this can give you the diagnostic accuracy of your test. Let's look at a very simple example. The people are going through the serum ferritin test. And let's say this is a number with the iodine deficiency anemia, and this is without anemia, right? So these are the numbers, and these are levels of the serum ferritin, right? So how to plot the ROC curve for this kind of data? So you can even manually plot, although it is any software will plot, but you can manually plot itself. For example, if I say I take cutoff point as 34. If you take cutoff point as 34, less than or equal to 34 and more than 34. So I have to collapse these. I can add these two observations, and then these two observations, so that I can get a 2 by 2 table. So last three and first two and last three. If you combine them together, you can get this table, right? So again, you are getting a 2 by 2 table, and for that you can compute sensitivity. The formula I have already given. You can compute specificity, multiply by 100, you will get in the percentage form. This is for cutoff 34. But there are many cutoffs which can be taken. 15 is one cutoff, 64 is another cutoff, 94 is another cutoff. So if you take all the cutoff and do the same thing, you will get sensitivity, you will get specificity. And this is sensitivity, this is specificity, then you compute 100 minus specificity. 100 minus specificity, and you will get all these values. And what is ROC curve? ROC curve is nothing but a plot between sensitivity and 100 minus specificity on x-axis and sensitivity on y-axis, and you will get this type of plot. And these are the indicators how you can predict. Let's say your area under the curve is between 0.9 to 0.99. It is an excellent test. It is between 0.8 to 0.89, good test, fair test, and this is useless test. So you can look at the diagnostic accuracy of your test. Okay, now I'm coming to the last part. Just give me 5 minutes, I will finish up. And sequential kernel association test. What do you mean by sequential kernel association test? You see, if you go through, it can be used for rare as well as common variants. It can be used rare for detection of the rare as well as common variants association. So this is important to see the association between genotypes and phenotypes. It is very flexible, computationally efficient, and based on regression approach. But the most important that it can include the different directions as well as magnitudes of effect. If you look at the C alpha test, or you look at the weighted sum test, or the other test, they are known as burden test, where either they look into the direction or they look into the magnitude. But these are, they can look into the variance direction as well as magnitude. That's why sequential kernel association test is very important. And it tests for association between variants in the region, both common and rare, and dichotomous. That is a case control or continuous phenotype could be there while adjusting for covariates, such as the principal components or maybe age or gender, etc. So all these flexibility is there. Okay. So it is based on the variance component score. There is a lot of mathematics involved. And one of my students has done a complete PhD on using this procedure on sequential kernel association test. We have conducted many series of tests using different data sets and come out which kernel is best and which kernel can be used for many of the association tests. Okay, and you can do power calculations. You can look into the sample size calculations. So all these things are possible using SCAT. So SCAT is a supervised test for joint effect of multivariate variants in a region on a phenotype. And regions can be defined by the genes. It could be a candidate gene or the whole genome studies or moving windows across the genome. And for each region, SCAT automatically calculates a p-value for association while adjusting for covariates. And your covariates could be like age, gender, ethnicity, etc. So how this model works? So for any individual, let's say ith individual, I look at a particular, let's say it is a case or it is a control. So yi could be either 1 or 0, right? Then there are different type of covariates like age, gender, ethnicity, etc. So that can be included as the covariates. So this is a vector of covariates. Then you have the genotypes, and genotypes are coded as in terms of SNPs. You can write say 0, 1, and 2. So denotes the genotypes for the p variants in the region as 0, 1, and 2. And dominant and recessives can also be considered, right? So this type of model, if you have your dependent variable as a continuous phenotype, you can include this as yi. But if it is your phenotype is actually case or control type, then you can, it's a dichotomous variable, you can use a logit model. But in both, the right side is almost similar. You can see this is without error term, this is with the error term, but beta is there. Beta represents the association, I mean the coefficients of genotypes, and alpha represents the coefficients of the covariates, and this is a constant. So what we want to test in this model, we want to test whether what is the effect of, what is the association of genotypes with the phenotypes, where this is a phenotype in presence of the covariates. So the parameters gets estimated, and just to skip the mathematical part, I'll just show you which kind of data you can deal with. For example, this kind of matrix we have, this is a genotype matrix which you have, and your covariates, they could be, if it is a categorical covariates like gender, you can have 1 or 0. If it is a continuous, you can have some measurements. And your phenotype could be categorical in nature, like binary 1 or 0, or it could be continuous type of this. So you will be having this type of matrix on a large scale, and then we apply this SCAT procedures. So we have done data analysis for AMD study, where AMD is considered to be the phenotype, whether it is 1, if it is phenotype is there, if it is control 0, and genotypes are taken as, so we have taken 26 different type of genotypes with covariates as age and gender. We also look at included the expression levels, gene location, SNP locations, and after doing the entire analysis, out of the 26 different kind of genes, which prevalent in the literature that may cause AMD, we have identified that only 6 genes are important for AMD. So this we able to identify, these are given in red colors. So that is the application of these SCAT procedures, thousands of SNPs on a particular gene location, and you can see the associations. Chi-square, etc. test they will not work, but SCAT you can work with. And this is just a mathematics, how we apply different type of kernels. And you can do the power calculations using all these procedures. So power calculations you can do. So plots, we have also plotted different types by using different weights. Then these are simulation studies we have carried out for effect size and also for the odds ratio. We have also looked into the power calculations for different sample sizes. So these are the power calculations. And people, because our entire conference is on data science in biology, and people get confused, what is data science, what is machine learning. So here is an, I mean, pen, you can call this as a Venn diagram. What do you mean by actually this artificial intelligence? Artificial intelligence always comes at the top. You see, it allows you to machine to think. And what is then comes the inner circle, that is a machine learning. And they provide the statistical tools to explore data like supervised learning, unsupervised learning, semi-supervised learning. And then in the inner circle, you take the application of what is called deep learning. And deep learning generally uses the artificial neural network, convolution neural network, recurrent neural network. So they are used. And then what is data science? Data science is an intersection or the helm of all this. It is called data science. You have to include all to be a data scientist, you must be aware of all these techniques. And in addition to that, you have to be very clear about some of the techniques of the Bayesian inference, like statistics techniques, probability, linear algebra, differential calculus, fourth vector machine. And if you are working into biology and bioinformatics, you must be aware of different types of genotypes, phenotypes, and alleles, frequencies, and all these things. Then and only then you can apply data science in biology. So that is the entire crux of my talk, which I want to discuss, that there are many statistical methods which can be applied in bioinformatics, but one should be aware of where to use which type of statistical methods. Then these are the many other statistical packages. Generally, people use MATLAB, or they are use SAS, or they also use R. And of course, Python is very much in demand these days. And these are some of the references you can refer back to. So with this, I'll end up. I think I have taken maybe 2-3 minutes extra. Sorry for that.